I think if it doesn't get to here, it's because I'm not standing in the right place. But right now, it's not pointing to me. I don't know. Oh, there we go. Yeah. So, okay, so we did this example maybe last time. Yeah, right, last time. So we were talking about the syzygies of these three polynomials. In other words, we wanted all the linear combinations of these guys that are equal to 0, where the coefficients in the linear combination are polynomials. And we said that there's three easy ones that we can compute: tau 1, 2, tau 1, 3, tau 2, 3. For example, this means that y times x squared plus minus x plus y times this thing plus minus 1 times this thing is equal to 0. So we got these three things, these three syzygies, and I claimed this theorem that is due to Schreier, that these three syzygies generate all other ones. Okay? And that's what the plan is for today, is to prove this theorem. Okay? So theorem due to Schreier, if, by the way, it's very important that G1, G2, and G3 in that example over there are a Groebner basis. Otherwise, Schreier's theorem is not true. But if you start with a Groebner basis with respect to some order, and you compute these pairwise syzygies tau ij, which are kind of the simplest ones that you can think of, then those tau ij are going to generate the syzygy module. Okay? And then I told you that I was going to add a furthermore here. And so this is the furthermore. Furthermore, this set of syzygies is a Groebner basis. This is bad, right? It is a Groebner basis for it. What do I mean by this? Let's call this module M. And so what I'm saying is that this set T is a Groebner basis for M. Okay? So what I'm saying is that these three guys over here, tau 1, 2, tau 1, 3, and tau 2, 3, are a Groebner basis for something. Now, that should confuse you. The reason that should confuse you is that for us, Groebner bases are things that live in polynomial rings, right? A Groebner basis is something that when you take the initial terms, they generate the initial ideal. By saying that these guys are a Groebner basis, somehow I'm implying that I know how to take initial terms, but I don't really know that. I haven't told you how to do that. And so what we need to do is basically learn how to take initial terms and how to do term orderings and things like this, not only over polynomials, but over free modules, which is what I was telling you last time. Okay? And so that's my plan. So, and if you're writing this down, then you should leave room, this much room in your notebook, because I need to say something else here. But it'll confuse you if I write it right now. So I gave you a quick review of modules yesterday, and a definition that is very important is that an R module M is free. Basically, if it's R to the something, okay? If it has a free basis E. So what I mean by this is that E generates M and there are no relations between E. So E satisfies no relations like R1 E1 plus etc. plus Rn En equal to 0, where the R's are in my ring and the E's are in my module. Okay? In other words, this is really more what a vector space looks like. We're used to thinking that vector spaces have a basis of things E1 up to En that generate and that have no relations between them. Okay? We saw that modules are more complicated than vector spaces, but free modules are kind of the easy modules that are more like vector spaces. The nice thing about this is that free modules are just They just look like this. Okay. And what I mean by this is that you can, I don't know, for example, if E is finite, usually we're going to care about finally generated modules. Okay? And so really when I say a free module, you should just think R to the n. Okay, so the finally generated modules, finally generated free R modules are just basically R to the n, right? Which is the example that we talked about last time. Yeah? Satisfies no relations. Thank you. And this is generates. No, thank you. Keep calling me on those things. You've seen that my R's sometimes look like I's, like this one. Or I guess last time I wrote Shiayer. This is an R. Okay. But so, for example, those guys tau 1, 2, tau 2, 3, and tau 1, 3 that I have over there, we can think of those as elements of the module R3, right? Okay. But remember that here we're thinking that R is just the polynomials in x and y. Okay, so that's a free module. And now, basically, what we are going to do is that we have a theory of Groebner basis over R, over polynomials. But I want to extend that into a theory of Groebner basis for R to the n. In other words, for n tuples of polynomials. Or if you find that you care about infinitely generated things, then you can do this for any e. But just for clarity, I'm going to stick with n, and you should know that everything works for e also. So, okay, so this is basically what I want to do now. Groebner basis over free modules. So first of all, we basically start with the way we started the class, and we just do everything over, but instead of R, we do it with R to the n. Okay. So let me say that R is the polynomials in x1 out to xr over some field, and let's say that my free module is going to be R to the n. Okay. And I'm going to choose a basis for it, so that this is going to be RE1 plus, etc., plus REn. So my basis is E1 up to En. Okay? So this is my free module. So the first thing I should do is I'm after a definition of monomial order, so we should say what a monomial is. Okay? So a monomial is basically something that is a monomial and only involves one of the coordinates. Okay, you should think of these guys as so if f is in f, then you can think of it as a column vector like this. Okay, and so a monomial is going to be something that is a monomial in one of the coordinates and 0 everywhere else. So monomial is something like x1 e to the a1 up to xr ar e sub I. Okay, and so this is just a usual monomial in our polynomial ring times a unit vector. Okay? And when I say a term, I'm going to mean a monomial with a coefficient that is a scalar in f, right? So lambda times monomial times EI, where lambda is a scalar, M is a monomial in R, and EI is a basis vector. Okay? And now I need to define monomial orders. Okay? And the reason that I need to do that is because I'm about to prove a theorem saying that tau12, tau13, and tau23 are Groebner bases. In other words, that their initial terms generate something, right? And so I need to decide what are the initial terms of these guys. Okay, so what should it be? Well, again, we're going to allow ourselves some generality. So a monomial order is a total order on the monomials of f, which is r to the n, but it should satisfy some properties. And the properties are going to be almost the same as before. So if some monomial, and now I want to write them like this. So this is a monomial in variables, and EI is my basis vector. And this is so in other words, this is a monomial in f, and this is another monomial in f. So if this guy is bigger than this guy, then when you multiply by an ordinary monomial, then that should still hold. So this is for M, a monomial in R. Okay. And the other thing is, remember before we had that M should be greater than 1. And now, well, that doesn't make sense because these are not monomials in F. But what are monomials in F are things like this. And I think what makes sense is to demand that MEI should be greater than 1 times EI. And so these are going to be the two conditions for a monomial order. Okay, this is fairly general, but what are the examples? How do we generally like to do this? So the easiest example is basically that you're just going to say, for example, that the monomials in the first coordinate are the most important, then the ones in the second coordinate are the most important, etc. So all monomials involving E1 are going to be bigger than all monomials involving E2, etc. And then within the monomials involving E1, you just choose an ordinary monomial ordering of your polynomial ring to decide what's more important. Okay? So here, and here, and here, you're just going to use a usual monomial ordering. On the polynomial ring. Okay? So maybe it's good if we do that in this example. So for example, let's say that I use the order where everything times E1 is greater than everything times E2 is greater than everything times E3. And then for each one of these guys, I'm going to use the lexicographic order with x bigger than y. Okay. So what I'm doing is I'm saying, okay, tau12 is a sum of monomials. What are the monomials? They're y E1 minus x E2, y E2, and minus E3. So what's the most valuable one there? Well, the ones in E1 are the most important ones, so I start there. And here I only have one, and so that means that this is going to be my most valuable monomial here. And then I do it here, so the monomials are y cubed E1 and minus x squared E3. So this is the most valuable one. Here, there's no monomial in E1, so I have to go to E2 and then decide what's the most valuable in level 2, but there's only one monomial, and so it's this one. So that's how I'm going to choose initial polynomials with respect to these orders. So this allows me to, so this defines the initial polynomial of f for actually, you see, I'm used to terminology that doesn't apply here. I call it the initial polynomial, but that's not true because this is not a polynomial, right? Because, for example, the initial term of tau 1, 3 is not y cubed. It's y cubed E1, okay? Which is not a polynomial. It's a vector of polynomials, okay? And so now instead of calling these initial polynomials, we should be calling them initial terms, or initial monomials, but not polynomials. You want to be careful. Okay, but then with this definition, then we can do Groebner basis again. So we say a Groebner basis for, before we had an ideal in our polynomial ring, right? But now what we have is not a polynomial ring, but a free module. And instead of an ideal, I'm just going to allow any module here. So for a submodule, M of f, with respect to some order, is a set of polynomials M such that the initial module of M is generated by the initial terms of G1. Okay. So the same definition, just in a more general context. So then I say, then we have to ask ourselves if everything that we did already applies, and it turns out that it does. So for example, what is long division? By the way, I should tell you that I find that the trickiest part about understanding all of this is just to keep track of what's supposed to be in where. So what's a vector, what's a polynomial, etc. And so I told myself that I was going to follow a convention, but let's see if it doesn't get annoying. But I'm going to try to follow the convention that whenever it's a vector, I'm going to draw it in a little column thing like that. Okay. So these guys are, you can think of as column vectors if you want. So, for example, long division, what did that say? Well, that was about dividing f by a bunch of polynomials, right? But now these are not polynomials, now these are vectors. Okay, and so each one of these things, I'm going to put a little box around it to signify that they're vectors. But I can still perform the same algorithm in exactly the same way. I can still do long division. And it still looks like this, but this is the kind of place where you want to be careful. So these guys are vectors, right? Now what about the A's? What are the A's? Well, the A's, you don't really have a rule of multiplying vectors, right? The A's are supposed to be just polynomials. Okay? Which is why I'm not putting a box around them. They are polynomials. But R is the remainder, and this is an equality of vectors, so that means that R needs to be a vector. Okay? So where the A's of I's are polynomials, but R is the remainder, which is a vector. Okay? And the properties that the initial term of f is greater than or equal to the initial term of ai times gi. And the other property was that no monomial of R is divisible by an initial monomial basically no monomial in R can be expressed in terms of the initial guys of this. Right, so this is no monomial of R is in the module generated by these initial terms. And how do you prove this? In exactly the same way that we proved it for polynomials. You just draw little squares around and make sure that everything behaves, and it does. There's really nothing else to say there. Okay.
And we assume that the G's are Groebner basis.
If the G's are a Groebner basis, then you have that R is unique. So it's the same as before. Remember that the way we use that is so that we could apply this algorithm of Buchberger to see if you have a Groebner basis or not. And to do that, we had to define. We simply had to check these guys, right? But what does this mean now? Because these are vectors now. Well, remember that the point of S of gi gj is that we wanted to cancel the leading term of gi with the leading term of gj. Okay? And we're going to try to do that. But the thing is that gi is a vector, and its leading term is in one of the coordinates. And gj is a vector, and the leading term is in one of the coordinates. If they happen to be in the same coordinate, then we can perform that cancellation. But if the initial term of gi is in the first coordinate and the initial term of gj is in the second coordinate, then there's no canceling to be done, and there's not going to be a relation there. And so the way that this is defined is basically that if the initial term of gi and the initial term of gj involve the same coordinate, EU, then we do what we did before, exactly in the same way. I guess this was mji minus mij gj. Okay. But if they don't involve the same coordinate, then you have no hope of canceling that. Okay, and so then you just give up. 0. But what's 0? I have to specify it's the 0 vector, right? And then, with this definition, we also have Buchberger's criterion, which says that if you want to check if something is a Groebner basis, just compute these guys and reduce them modulo g. If they reduce to 0, then you are a Groebner basis, and if they don't reduce to 0, then you are not. That's the criterion. And the algorithm tells you what to do in that case. Just keep throwing remainders in until you finish. And this all works in the same way. In exactly the same way. Okay? Okay, and so now I'm finally almost ready to say my theorem. Because now you see we can make sense of the idea that these guys are our Groebner basis. Because now we know what that might mean. What I haven't specified is what order you're supposed to consider. And that's what's missing in that statement. Okay, so let G1 up to Gm be a Groebner basis for whatever module they generate. Okay. Then I define the syzygy module. I was watching my lecture yesterday and realizing that I wrote this wrong, but in a silly way. I think you could tell what I meant. So the syzygy module basically tells you what relations are equal to 0. Okay? So they're going to be the m tuples in R to the m, such that a1 times g1 plus etc. plus am times gm is equal to 0. This lives in R to the m, right? I want to give a different description for m, which is that m is the kernel of this map. I can define a map from R to the m to my module to switch notation here. Let these guys be a Groebner basis for m, and I don't want to call this guy m. So m is the module that G1 up to Gm generate. So I want to define a homomorphism from the free module R to the m to the module m, which is a submodule of R to the n, let's say. And you should think about that example over there while I do this, right? So in that example over there, n is equal to 1 and m is equal to 3. So m is the kernel of the map that takes, I don't know, let's say that R to the m has basis epsilon 1 up to epsilon m. Okay? And then I'm going to map each basis vector to this gi. And this is where it's easy to get confused, and this is why actually, if you see, I made this a blue box, and I meant to do that. Because there's vectors of two different sizes now. Right? We have things that live in R to the n and things that live in R to the m. Question?
So M is no longer the kernel of the above thing.
Sorry, so it is the kernel. So this is the kernel of this. Thank you. So the syzygy module is the kernel of this guy, where this is a vector of a different length, probably. I guess if I want to be consistent with my notation, then I should put a little box around these guys. These are 1 by 1 vectors, okay? But that doesn't mean they're not vectors. Okay? So hopefully with that you see what I mean by this. Why is this true? Because basically if epsilon I goes to gi, then the vector a1 epsilon 1 plus etc. plus am epsilon m goes to a1 g1 plus etc. plus am gm. And so that means that this guy is going to be in the kernel if and only if this guy is 0. Okay. So this is another way of understanding the syzygy module. Okay. And now, just my last piece of notation, I'm going to say that when S of gi, whenever we do this Buchberger thing, right? And this tells us to take mji gi minus mij dj. And because it's a Groebner basis, then we're going to get something that can be expressed in terms of the g's. And remember that we wrote this like this. The sum over u. Okay. So this is how it looked before. Now these guys are vectors, but nothing else changed. But for each one of these things, I'm going to define this element tau ij. Okay? I'm going to define it to be so it's supposed to be something that lives in the syzygy module, and so what it should be is just this guy, except that instead of the g's, you need epsilons. Now these guys are just living in a different space. Okay. Again, if you're confused about this, you're probably confused about the notation and not about the content. So let me tell you why that is. Because I'm just giving. We're talking about relations in two different ways, right? So I'm telling you that tau 1, 2 is a syzygy. When I write this, I'm writing exactly what I wrote in the bottom line of that board. Okay? It's some vector. Tau 1, 2 is some vector. But the way that you should be thinking about that vector is that this is a vector that makes this a true equation. And this is my first description. Okay? So I wrote two long equations over there. The first one says yx squared minus this times this minus 1 times y cubed equals 0. And the other equation is not really an equation. It's just saying I want to define tau 1, 2 to be the vector that certifies that equality. So I'm just keeping a notational difference between a vector and an equation. Okay? That's all there is to that definition. Okay, and then finally I can state my theorem, which says that this set of basic syzygies is a Groebner basis for all the syzygies. With respect to what order? With respect to the order given like this. Where is this order supposed to live? Well, in that case, it lives in R cubed, right? It lives in R to the m. It's an order on the epsilons. Okay. So I have to decide when a monomial times epsilon u is less than a monomial times epsilon b. Okay. And this I get to choose. The only thing is that I just need to be careful that I do define a monomial order. Right? But then I'm going to define this by saying that switch to greater than. So I'm going to compare these guys by using this comparison. So I started with a comparison in r to the n. Okay? So in that case, it was just a comparison in r to the 1. And I'm going to use that comparison here. Sorry. So I'm going to say, if you want to compare these two monomials, then just replace the epsilon u for gu, replace the epsilon v for gv. Then this is some vector of polynomials. This is some vector of polynomials, and these polynomials are r to the n, are in r to the n. They're kind of black vectors, right? And this order is an order in r to the n, which means that I know how to compare these initial terms, and so I compare them. If this guy is bigger than this guy, then you say that this is bigger than this. But if they happen to be equal, then you have to do something a little bit different. So if that test is not conclusive, if you compute these two initial guys and you find that they're the same thing, now when can you not compare two monomials? Basically, when they're the same monomial, except by a scalar, maybe. Up to a scalar. And if these guys are equal, then this test was not conclusive, and then you're just going to decide that you're going to go by whatever subscript is smaller.
This is supposed to be an n in it?
This is n, yeah. Okay, so this is some definition of an order. It's a little bit complicated. I would suggest that if you want to understand what this is saying, then the best thing to do is just do it in that example. And so for each one of those guys, tau 1, 2, tau 1, 3, tau 2, 3, we're exactly in this setting, right? The idea is that we started with a Groebner basis here, and this lives in f in r to the 1. And there we have an order that we're comfortable with. And then what I'm giving you there is some definition, which is a little bit complicated, that tells you if you know how to order things in r to the 1, how are you going to order them in r to the 3? Which is where this computation lives. Okay. And so there's a rule of going there, and it's that rule that I'm describing there. And so what I'm saying is simply that if G1, G2, and G3 were a Groebner basis with respect to the order that you were using here, then tau 1, 2, tau 1, 3, and tau 2, 3 are going to be a Groebner basis for this guy according to the complicated order that this guy inherits from this guy. That's what the theorem is. So if you have any questions about the statement of the theorem, now would be an excellent time to ask them. I won't need this stuff. Question? No. So this is some Groebner basis. But we know that you might have different Groebner bases for the same ideal, and here it's also true that you might have different Groebner bases for the same module. But this is just giving you one. I'm sorry? Yeah, and then you can reduce it, and you would get the unique reduced Groebner basis. Yeah?
So if we, in this example, if we pick a different Groebner basis and use the same ordering tau?
That's a very good point, actually. If you pick a different Groebner basis, then not only are the taus different, but this order is different. Because if you see the way that I'm defining the order, G plays a role in that order. Okay? I'm saying that you compare M epsilon U and N epsilon V by doing something with G. And so that means that this depends on G, this step. So if you switch to a different Groebner basis, then you would get a different Groebner basis here with respect to a different order, probably.
Are we just fixing a basis for R to be N? I mean the epsilons of U and V?
Yes.
So it depends also on the basis?
Yes. Right. Any other questions? Okay. Now you should remember that there's two statements here. One that's very simple and one that's more complicated. So the first statement is any syzygy is generated by the stupid syzygies. And the second statement is that the stupid syzygies have a very nice property that allows you to compute. Okay. So I'm going to start to prove this, and basically what I need to do is take any syzygy and show that it's a consequence of the easy ones. So how do you prove this? Let's first do it in an easier case, which is when these guys are all monomials. First we do it in the case where the i's are monomials. Okay. So I say take some syzygy. Take a syzygy tau, which I can write as A1 up to AM. Okay. And what this means is that A1 G1 plus AM GM is equal to 0. And I guess to be consistent, I've been making this a column vector and coloring it blue, right? By the way, I don't know if you're finding these pictures and these color codings useful, but if you are, you should fill them into your notes because I didn't do it in my. I just thought of this on the way here that this might help. So, oh no, this is not the place. So we take a syzygy, and then we have to reduce it to one of the simple ones. Okay? Well, what I'm going to say is this. I'm going to say this is an equality of vectors of polynomials. And that means, first of all, that you have equality in each level, right? In the first coordinate, and the second coordinate, etc. And second of all, you know that you have some polynomial equal to 0, and that means that you can take the coefficient of any monomial, and it has to be 0. So what I'm going to do is consider the coefficient of any monomial that maybe looks like m times EU. Okay. Above. For example, I might be looking for all the x squared y's that I see in the third coordinate. Well, then, if I see what happens there, I'm going to have an equality like this. With this guy fixed, I'm going to have that summation So I only look at the u coordinate. So that means that.
Can you say what you're writing? I can't see it all. You're writing, so we're like, you know.
I'm sorry?
When you stop talking, I can't see what you're writing, and then if you say the next thing, I can't understand what you're talking about.
Okay.
So talk a little more.
Yeah. So I'm going to consider only the youth coordinate, right? And so in the youth coordinate, I have that a1 times g1 sub u plus am times gm sub u is equal to 0. That's in the youth coordinate. But I'm saying more than that, because I'm saying not only look at the youth coordinate, but also look only at the things that have total degree m. Okay? This is a polynomial, this is a polynomial, and so I'm only going to look at the part of this polynomial that contributes to the monomial m. And so that's going to look like this. It's going to look like some constant multiplied by some monomial and multiplied by some other monomial. And I do that in each guy. What am I saying here? The thing is that these GIs are monomials, right? And so there's two things that I should say. First of all, each one of these GIUs is going to be either a monomial or 0, okay? Because the vector GI is a monomial vector, meaning that it has a bunch of zeros and one monomial. When I extract the youth coordinate, I'm only going to get either a monomial or 0. Okay? And that means that if I now look at the things of degree m, then the only way that this guy is going to contribute in degree m is if I multiply by some monomial n1, such that when I multiply by this monomial, I get exactly m. So ni is a monomial such that ni times gi sub u is equal to m. Is, I'm sorry?
That's NIGIU degree. What are the alpha i's? What are the
M.
what is the
So the alpha i's, and alpha i's are just constants in the field. So what I'm saying is that if you want to make the monomial m here, then you have to consider the term that contributes m over g1u. And that's going to come with some coefficient alpha. So that's how I define that. Okay. So alpha I is the coefficient of ni in ai. Yeah?
Pretending I don't understand notation at all. Basically what you're doing is you have these alphas and these n's and these z's, and all they do is they contribute to sum up to be m and nothing but m.
Yeah.
Okay,
So
I'll accept that.
yeah. So what I'm saying is just look at only the contribution in the youth coordinate and only the contribution in the monomial m, and delete everything else. And then I get some equation that looks like this. Okay? So then I'm going to say this. I'm going to say that what I need is to get that this syzygy is a consequence of the basic syzygies. Okay? By the way, if this equality is true, then it's also going to be true if I don't take youth coordinates. Well, maybe let me just leave it like this. So I want this to be a consequence of the basic syzygies. And so what I do is that I'm going to express this guy as a consequence of the basic syzygies. Okay? How do I do that? Well, I induct on the number of alpha i's, on the number of alpha i's that are not 0. Okay? And let me just say very quickly what I do. If there's no alpha i's that are 0, then that means that there's no equation there. And so that's obviously generated because there's no equation. Now, there can't be exactly one alpha I because you can't have a sum of exactly one monomial equal to 0. If something equals 0, then there must have been cancellation. Okay? So there must be at least two alpha i's that are not 0. So suppose that alpha I and alpha j are not 0. And that means that I have a contribution alpha I ni gi u and a contribution alpha j nj gj u. Okay? And these are part of my equation here. So this includes things. It includes this. But then what I claim is that if you look at what equation tau ij says, well, what does it say? It says I want to find a syzygy between gi and gj. Okay? Now, if these guys are non-zero terms, that means that they have a non-zero entry in the same